Hello everyone, today let's talk about parametric surfaces. We have seen surfaces given in the explicit form and implicit form. There is also a parametric representation that we can use to describe a surface, in the form of a vector function r of uv. This vector function gives the position of a point on the surface when specific values of u and v are chosen in their respective domain. One thing to remember is that there are two parameters in the parameterization. To see why we need two parameters, we can first look at the parameterization of a portion of a plane, bounded by a parallelogram. Let's say we already know these three vertices of the parallelogram, P, Q, and R. Notice that the line segment PQ is an edge of the parallelogram. And if we want all the points on this line segment, we can use the parameterization R1, which starts from the point P and follows the direction vector PQ to point Q. We can obtain the adjacent edge PR in the same manner, and it is given by the parameterization R2. Now, to get all the points inside the parallelogram, we need to start at every point on the line segment PQ and follow a line segment parallel to PR to this edge. For example, we know that point A is a point on PQ. If we start at this point and follow a line segment to the opposite edge, we need to add s times the vector negative 1, 3, 1 to its position vector, giving us this. To view the whole parallelogram, we need to do the same for every point on PQ, which means adding the vectors r1 and s times negative 1, 3, 1, using this vector function. Many textbooks are using u and v as the parameters. So if you want, we can rewrite this parameterization as this, which is just replacing t and s by u and v respectively. So now we understand why two parameters are needed to generate a surface. Next, we will be looking at some common surfaces that we wish to parameterize. Since we already have parameterized a portion of a plane bounded by a parallelogram, we can try parameterizing the whole plane. Say z equals 3x plus y minus 2. We can use x and y as the parameters. That is, let x be u and y be v. Substituting this into the equation, we get z equals 3u plus v minus 2. And we have our parameterization. In fact, for any surface given in this explicit form, we can use x and y as the parameters, and parameterize the surface as u, v, f of uv. For example, for a paraboloid with this equation, we have uv as xy, and z as 4 minus u squared minus v squared. Now, let's say we want just a portion of this paraboloid. Then all we need to do is to restrict u and v. So we can try restricting u and v to be between negative 2 and 2. Looking at the xy plane, we can see that the domain is a rectangle. Notice that some part of the surface is below the xy plane. You may ask, what if we want only the portion of the paraboloid that is above the xy plane? That will mean we need the domain to be a disk. So we can use cylindrical coordinates. As you can see, setting z equals 0, we get this equation, which is a circle in the xy plane. With that in mind, we can let x be r cosine theta, y be r sine theta with such parameter domains. And plugging into x and y, so z becomes 4 minus r squared. We want r to be between 0 and 2 because we want all the points on this circular traces of the surface. And theta between 0 and 2 pi will give us the complete circles. So our parameterization is this. If we want, we can replace r and theta by u and v, respectively, thus giving us this expression. How about a sphere? Say x squared plus y squared plus z squared equals 25, which is given in the form of f of x, y, z equals 0. The easiest way is to use spherical coordinates. That is, by letting x be phi sine phi cosine theta, y be phi sine phi sine theta, and z be phi cosine phi. With the parameter domains, we get the whole sphere center at the origin, with radius 5. If we want only a portion of the sphere, for example, just the shell in the first octant, We still use the same x, y, z, and we restrict the parameter domain phi and theta both between 0 and pi over 2. Or, if we want only the bottom hemisphere, phi will be between pi over 2 and pi. Next, let's look at the differences between a circular cylinder and a circular disk. You may say, they look really different if we graph them. True, but when it comes to parametrizing them, we can easily get them mixed up. To parameterize the circular cylinder, since the horizontal cross sections are circles parallel to the xy plane, we have x equals 2 cosine u, y equals 2 sine u, and z equals v, with u between 0 and 2 pi. Comparing with the parameterization of the circular disk, x equals v cosine u, y equals v sine u, and z equals 0, with u between 0 and 2 pi, and v between 0 and 2. Notice that for the circular cylinder, we want all the points that are 2 units away from the center of each of the cross-sectional circles. So, when we use cylindrical coordinates, r is fixed and equal to 2. On the other hand, for the circular disk, since we want all the points on and inside the boundary circle, we chose v as r and let it vary between 0 and 2 inclusive. Lastly, let's consider the circular cylinder y squared plus z squared equals 9. Notice that for the vertical cross sections are circles parallel to the yz plane. So we have y equals 3 cosine u, z equals 3 sine u, and x equals v, with u between 0 and 2 pi, and v unrestricted. We'll talk more about parametric surfaces next time. If you like this video, please give a like, subscribe, and share it. Thank you for watching. I will see you next time.